So it is started. Over to Mr. Nishant Gupta for the webinar. Thank you.
Good afternoon, friends. I'm Nishant Gupta from Degree Day Private Limited. I'm Managing Director of this firm, and we operate to provide all 360-degree solutions related to HVAC. It's an honor to be part of ISHRAE, and I'm happy to have all of you with me today. We'll be talking on some concepts which probably we had been listening but never had a chance, or probably do not have this often a chance to interact and understand on the concepts of so-called green conditioning. Now, why I've named this as green conditioning, uh, we'll take it forward and try to understand next 1 hour to rethink the way we design the air conditioning system. Well, we had been talking of green. Very often you had been reading in newspapers and dailies on various talks and seminars. But why do we talk of actually the topic green? Global warming, again, the buzzwords, save the environment, energy saved is energy produced. It does affect to you or to the society on a larger platform when we are talking of it does affect my planet, my country, or my environment, but it starts really bothering to you as an individual when it starts affecting your health, your comfort, and your money. Uh, I'm changing to a slide which probably similar to this, you might be seeing it very often, which talks of climate change. This helps me to recall an incident which happened during this summer where my son was given homework and he was asked to get back to their parents and grandparents to understand how they used to spend their summer vacations. He came back to me and asked, and I was telling him that we used to go to our friend's place, used to play cricket, we used to go to our uncle and aunt's place. And then he went back to his grandfather and asked that, what do you used to do during your summer breaks? So to my surprise, his grandfather informed that wherever they used to live, there used to be jungles, there used to be rivers nearby, so they used to climb on the trees, uh, swim in rivers, and enjoy their life during their summer vacations. Very often nowadays, when we are moving on the roads and crossing one border on another, we do see these rivers which are primarily not flowing as they used to happen earlier. Not a very old story, maybe 30 years, 40 years before, but the scenario has really changed. And somewhere we are actually responsible to it. So what can we do to save this? Of course, we can conserve energy. We can spread the awareness. We can use eco-friendly systems. But as a HVAC designer or a user or a recommender, it is time for us to revisit our so-called energy guzzlers, the air conditioning systems. So today's objective would be to discuss or touch upon the basic concepts of IAQ, which is the air quality, thermal comfort, the fundamentals of evaporative cooling, non-conventional alternates of evaporative cooling, may it be a direct evaporative cooling or indirect direct or a hybrid, and we'll try to see some case studies to relate on those topics. When we come back to the topic of indoor air quality, well, there are many things which are associated to it. There's a common term which you might have observed, which talks of sick building syndrome. Now, this is something which, if you go to a place and come back ill, it could be because of multiple reasons, and this is what the building gives you some illness. So we're talking of reasons which could be inadequate ventilation, chemical contamination, or a biological contamination. When I say inadequate ventilation, of course, as air conditioning guys, we provide fresh air or design fresh air as per whatever ASHRAE 62.1 or whatever norms we are following as per ISHRAE and ASHRAE. But at the end of the day, if somebody wants to save power, and he would simply go at the operator level and switch off that fresh air damper. So till the time the indoor concentration of carbon dioxide doesn't exceed 600 ppm, you are still okay with that. But the moment it starts increasing beyond that, you start having problems related to respiratory diseases or maybe difficulty in breathing, headache, sweat, fatigue. In fact, there have been studies done by all these IT companies which shows that if the building is having a required fresh air, the amount of absenteeism has reduced, the amount of output of the individuals working in their company have increased. So IT companies where they are actually paying on per hour basis on man to man, so definitely it affects a lot in their business. Another factor that we had been listening very frequently, and particularly up there in the north during winters, is of PM 2.5. Now, this particulate matter 2.5 is actually that small particle which goes deep inside our lungs and develops risk related to cardiovascular and respiratory diseases. If you see a depiction on the right hand side over here, the gray thing is a kind of hair which is typically of the size of 50 to 70 micron. The blue lines are actually showing, that blue dot is showing a PM10 particle, and over that there is a circumference of this uh, orange or red dot which is showing PM2.5. Now, this PM 2.5 and PM10, there are guidelines by WHO which says that in a developing country, typically the range of PM10 is in the range of say 70 micrograms per meter cube. And while as per the WHO, the guidelines is that it should remain well within 20 micrograms per meter cube. So they say that if this is being maintained, the deaths related to pollution can reduce by up to 15%. While we're talking of this 20 and 70, you'd be surprised that when we refer to our actual outdoor conditions and go back to there in North India during this December and January, you would find these Pradushan ka live meters on the main roads, and the pictures are actually showing the story where the PM10 count is 484, and there was a time during Diwali where it went off to go even beyond 1500 and 1900 ppm, which is like extremely dangerous. We had been reading on the newspapers and watching on the television news that the cricket matches are on hold, or maybe the schools are having holidays. Government has issued guidelines not to get out from your place. So outdoor air is always not fresh air. There's a difference. The point here is that when we are giving this outdoor air in the system, it is not actually fresh air. It needs to be treated properly. At the same time, if we are not having adequate ventilation, chemical contamination is there, which also affects to us. We have a tendency of smelling this typical ethane, methanes when we paint our house or when we buy a new car. So there's off-gassing which happens from all these new items which are there, and that is what is volatile organic compounds are, and they do affect our respiratory related diseases. So there are some steps which we can take to reduce the exposure, which could be a source control, that is either we remove or reduce the number of products which are off-gassing, or we can increase the ventilation. But then in doing so, we are also increasing the power consumption of our air conditioning system. Similarly, when we're talking about biological contamination, there are studies which talks of that when a person is sneezing, you can see in the pictures that what are the particles, number of particles which is getting out from your mouth or nose, and what is the distance that it can travel. It can actually be in excess to million of particle, and it affects more than one ways, and the problems related to say swine flu and various other issues, bacterial or virus spread happens because of the biological contamination. And when we are residing in a air-conditioned environment, this problem actually multifolds. If you go back and remember to one of the articles which was published in ISHRAE journal while this 9/11 happened, and Taj property was kind of it was undergoing a renovation. The most expensive suite fan coil unit duct was found to be covered by more than 50% by these bacteria, because this was like a hot, the humid and dark place where the bacteria find the best place to stay with, and the air conditioning uh, air is passing through this and related to troubles, which we typically call that as biological contamination. Whenever we are using air conditioning system, of course, the gas leaks, and may it be chlorofluorocarbons or HCFCs, they all relate to various troubles and generate that ozone holes. How it does it? It's a simple phenomena where this UV radiation hits the CFCs, and the chlorine atom breaks away. The chlorine atom hits the ozone molecules, the oxygen particles get away, and chloromonoxide is produced. That individual particle of oxygen again hits this chloromonoxide molecule, and that oxygen gets detached. Again, this chlorine is now free to get attached to another CFC, and that's how another ozone atom, and that's how this cycle continues and results relates to trouble. And it, of course, really relates to problems pertaining to increase in the temperature of air as well as the sea temperature, increase in CO2 levels, and various problems. So, to summarize this, the idea, what we are trying to communicate over here is that conventional air conditioning, without any doubt, provides us the perfect comfort conditioning, but at some cost. When we are not providing a proper indoor air quality, it is relating to troubles related to maybe CO2 concentration or sick building syndromes, or with the gas which is getting out, it is related to troubles of ozone depletions. So as a HVAC engineer, we are expected to deliver the best indoor air quality, consume the least amount of energy, uh, be a very good protective person for the environment, provide an absolutely perfect thermal comfort, but don't ask for money. That is what the finance guy would say. So that's what the challenge is for a HVAC engineer. You might have seen very recently in June, the National Cooling Action Plans and the Power Ministry also suggested that the air conditioning temperature should be increased. Uh, ISHRAE in its position paper had recently also published that air conditioning consumes as big as 40 to 60% of the total energy consumption in an air conditioned environment. So it's time for us to think that do we actually require air conditioning and do we actually require 22 degrees centigrade? Who has set this 22 degrees centigrade as the ideal parameter? And what do we actually mean with comfort, and what is our tolerance level when we are talking of comfort? So getting back to the subject where we are talking of, say, thermal comfort, uh, in the ISHRAE standard 10001-2016, it defines that thermal comfort as a condition of mind that expresses satisfaction with the thermal environment and is assessed by subjective evaluation. So thermal comfort of a human being is influenced by multiple factors. It could be apart from psychological, we are not considering as psychological factors, but it could be physiological factors like what is the age of that individual, what is the metabolic rate of that individual. A person of age of 70 years might feel comfortable at 26, 28 degrees or 30 degrees temperature, while somebody who's young or maybe exercising might not feel the same comfort even at 22 degrees centigrade. Of course, depending upon the clothing that they are wearing, it does affect the comfort. And on the physical parameters, which are normally in the control of a HVAC engineer, is air temperature, vertical air temperature difference, mean radiant temperature asymmetry, floor surface temperature, RH, and airspeed. All that has been well defined in the ISHRAE IEQ standard 10001. It also talks of adaptive thermal comfort. Now, this is a concept which, or a theory that suggests that a human connection to the outdoor and control over the immediate environment that allows them to adopt to and even prefer a wider range of thermal conditions than what is generally considered as comfortable. Again, ISHRAE in their standard provides minimum requirement of acceptable thermal indoor environment, which establishes the range of indoor environmental conditions that are acceptable to achieve thermal comfort for occupant. Long back, when ISHRAE logo was the old logo that we are seeing now in the picture over here, Chennai chapter has released a flyer which was advocating the set temperature of air conditioners to 27 degrees C in place of 22 or 24 degrees C. No doubt that it saves huge amount of power, and this is what was again verified, studied, and confirmed by ISHRAE IEQ standard, which says that operative temperature is in the range of, if it is in the range of 24.5 plus minus 2.5 degrees C, that is in the range of say around 23 to 27 degrees centigrade, it is considered as pretty comfortable for most of the occupants. So the temperature range of 26 to 27 has been found in many studies a very comfortable temperature. Way back in 2008, UNO also launched an initiative called Cool UN, wherein they suggested to increase the set temperature of the thermostat, and there was a campaign which was run so as to reduce the air conditioning loads. And they also recommended to remove the heavy insulated jackets and neckties which the dwellers were using, which helped to reduce the body temperature by up to 2 degrees centigrade and thereby allowing to set the room temperature to 27 degrees centigrade. ISHRAE, again, it's the recently published position paper on IEQ and IEQ standards, endorse that metrics such as effective temperature and operative temperatures are a better measure in comparison to just the normal dry bulb temperature that we measure. On the same lines, Power Ministry in June 2018 issued advice to the manufacturers to set the labels on air conditioners, which indicate that optimum temperature settings should be around 24 degrees centigrade. Similar studies was done by CEPT University in Ahmedabad while they worked along with the University of Technology in Sydney in 2014 and released a study called IMAC, which is Indian Model of Adaptive Thermal Comfort, where they informed that India has a trend of using 22.5 degrees centigrade as a set temperature, which is of course followed as per ISO standard and ASHRAE 55 standards. But the modern buildings which are designed to be sealed often are not able to take the advantage of the outdoor conditions. This elevates the Indian comfort expectations, and the dwellers have different kind of expectations. So they conducted a study on various kind of dwellers, those who are residing in an air-conditioned building called as AC, and those who are residing in a naturally ventilated buildings or NV, and also in a mixed mode building. So the study revealed that the person who's staying in an air-conditioned environment develop high expectation of homogeneity and cool temperatures. They become quite critical if the thermal conditions deviate. You would see in day-to-day business affairs also that if you're not able to achieve the desired result, even at a difference of 1 or 2 degrees centigrade, you keep getting a call from the dweller that there is a problem in air conditioning system. While somebody who's living in a naturally ventilated building that is without any air conditioning with windows and maybe with fans get accustomed to variable indoor conditions that reflect local patterns of climate change. The thermal perceptions, performance, as well as tolerance are also likely to be extended on a wider range. So the study concluded that the occupants, those who are residing in an air-conditioned building, showed lesser acceptance, while those who are staying in a naturally ventilated buildings shows a wider acceptance of comfort under various conditions. So air-conditioned dwellers want a temperature within 20 to 27, while in a naturally ventilated building, a person is still finding themselves to be comfortable between 80 to 30 degrees centigrade. The IQ standard also indicates, and similarly other government and institutional body, that if the comfort range for Indians were to be redefined, it is more likely to shift upwards. And while we are talking of changing our set temperature from 22 degrees centigrade to 27 degrees centigrade and maybe up to RH level of 70%, the impact on air conditioning system designs could be huge. It could be enormous, not only in terms of air conditioning set temperatures and their carbon emissions, but also giving different avenues to other alternate technologies to open up the doors and get used in the day-to-day affairs. So the concepts of passive cooling or evaporative cooling or geothermal technologies, they all become practical, and you start finding a lot of other avenues to air condition or green condition your premises. So green conditioning is nothing but opening and changing our perspectives towards the fresh air, the tolerance level, the adaptive thermal comfort, and for human well-being in a much more cost-effective way and in a much more energy-efficient way. So now coming back to one of the subjects that we are touching upon, the alternate technologies is air cooling, or the applied applications of the air cooling. It relates to me to one of the slides, which is from Berkeley's. This is the online site. You can actually view the current situation of the air quality index across the world. So I just pulled up, and you can see the historical pictures as well. So I just pulled back one of the images while I was talking in similar kind of seminar once in December, November, wherein the picture shows that the conditions in and around up there in the north, because the temperatures are low, outside it's smoggy, it's not very good. The outdoor air quality index goes to as high as 290 to 300 micrograms per meter cube, which is very unhealthy. And what happens in evaporative cooling, or when you're washing the air with the water, is something like this. So this is the snapshot which I've took at 1 p.m. today for India, which indicates the same locations. If you are referring back to Delhi, now the AQI has dropped to 67.2, just substantially low, and it has come to still a moderate range. And there are many parts of the country where you see that it has gone down to as low as between 0 to 10. So this is the impact of what happens when you're washing the air with water and your outdoor air quality improvisation, which happens across the world, not only over here. And this is live, you can see anytime online. So getting back onto the fundamentals, when we are talking of, say, evaporative cooling, I'll like to play a small video which shows that how the evaporation is happening. So just give me a minute and try to see this video. Okay, so you might have noticed that the water is getting evaporated. Now we have always learned, being studying this, that evaporation happens at only 100 degrees centigrade. So it's important to understand the difference between boiling and evaporation. How does the water evaporate when it is kept in the normal ambient temperature? So need to understand that ordinary evaporation is a very surface phenomenon. That is, some molecules which are having enough kinetic energy escapes by taking away the heat from the air, which is getting in contact with that top layer of the water, which is what is known as heat of vaporization, which is a cooling mechanism. Now, these molecules absorb the necessary heat and they evaporate in the hot air. While in case of boiling, since the pressure inside the liquid is equal to the atmospheric pressure plus the liquid pressure, that is the water which is, or the water molecules which is present at the bottom flask, has to undergo that pressure to reach to that surface and start evaporation. So at boiling point, that is in case of water at a mean sea level at 100 degrees centigrade, the saturated vapor pressure becomes equal to the atmospheric pressure, and that is how the bubble forms and the vaporization becomes a volume phenomenon. That is how the entire water in the complete flask starts boiling and evaporating. Now the human body has been made perfectly in sync with evaporative cooling concept. God has made our skin so as to continuously perspirate, and that is why at times when we are standing near to a swimming pool or maybe a sea, the breeze that is coming up is giving us a tremendous comfort. Simple example is that we start feeling that coolness while we are standing in and around that water bodies. It again follows the same evaporative air cooler concept, wherein the heat is being absorbed by the moisture or the or because of the water evaporation, and this evaporation actually draws the heat from the body and goes into the air to increase the humidity in the air and reduce the temperature of the surface. If you see a normal human being under seated condition would have a basal heat rate production of about say 90 watt, and assuming that his ambient is at 45 degrees centigrade, he would start sweating. So the sweating would happen once the surface temperature of the body goes beyond to what your body temperature is. So in this slide, we are seeing that because of conduction, maybe 8 watt is getting added up, radiation is adding maybe 109 watt, and adding the basal production of the human being, 207 watt is getting out from the skin. The convection effect would change based on multiple parameters, which is not very easy to calculate. This is just a general slide which depicts that how it is being calculated. So you can actually calculate the perspiration or the amount of heat which is required to evaporate the quantity of water from the human body. And very interesting analysis is that a human metabolic heat gains in an air-conditioned room would change from sensible to latent based on the room temperature. So in a scenario where somebody is seated comfortably in the office, the total metabolic rate is say 130 watt. So the ratio at 20 degrees centigrade is like 50 to 1 is to 2. That is, the sensible heat rejection is about 86 and 44 is the latent. While it reaches to around 28 degrees centigrade, the sensible part now becomes only 50 and latent becomes 81. So it does affect when the ambient temperature surrounding by a human being changes, the amount of heat which can be extracted from the sensible component and from the latent component. So we are talking of designing a adiabatic system or the air cooling system which can help us actually size the equipment to meet the requirement of the room. We can very well do it. Normally people had been doing it on a thumb rule basis of say 5 inches, 10 inches, 20 inches, 40, 60 inches based on their experiences. But it can very well be scientifically calculated. As you do your air conditioning heat loads, you need to put in the regular parameters. So I'm just showing one of the slides which is referring to uh, a factory environment wherein we are setting up the heat load conditions, which is like the area, the height, the volume, and we are calculating the total room sensible heat from the air conditioned space. We also need to understand that what is the acceptable room temperature by the dweller. So somebody asked for say 36 degrees centigrade, and you have calculated your heat load as say in this example around 4,40,000 or rather 7,000 BTU per hour. So you need to understand that what will be your supplier condition from the direct or indirect evaporative cooling system. In this example, let us consider that 28 degrees centigrade is my supplier condition, which any manufacturer can give you, and you can also very well check it and design it. We'll go back on to that in the next slides. So if 28 degrees centigrade under a defined outside temperature of RH, temperature and RH is the supplier condition, adding up the heat from the motor or from the duct, say 29 degrees centigrade is the supply air temperature from the machine, and you want your desired space temperature to remain well within 36 degrees centigrade, that is the delta T of 7 degrees centigrade. You can calculate the CFM of the evaporative cooling system, which is nothing but the room sensible heat gain in BTU per hour divided by 1.944, which is the conversion factor into delta T in degree centigrade. So this will give me a result of say 3,30,000 cubic feet per minute of air. This is what is required to achieve my room temperature, leaving air temperature of 36 degrees centigrade, provided that you have given the correct parameters in your heat load calculations. So you can very easily from your heat load calculation sheets pull out the content related to room heat sensible gain factor, not factor, the total RHS, and divided by the delta T, that is the supply air actual real temperature versus the room temperature, and 1.94. So how to calculate the supply air condition in case of evaporative cooling? Of course, if your ambient condition is say T1, which is 40 degrees centigrade, and the ambient RH is 10%, the evaporative cooling would always follow this constant wet bulb line, which depending upon the kind of evaporative cooling machine that you are selecting, rather the cellulose pad or your cusp pads, whichever you are selecting, based on their saturated efficiency, you'll come to know that what is the supply air condition. So in this example, here we would see that our total supply air temperature would go down to 23.6 degree if it is operating at an efficiency of close to 65% with a wet bulb of 19 degrees centigrade. So you can calculate from the psychometry that what is my leaving air condition. Once you know that what is your leaving air condition, you can put it back into that heat load calculation sheet divided by 1.944 and delta T so as to come to the air quantity which is required. Now, the cellulose pads which are being used are also different types. The common ones which are used in the market are 7090 and 5090, wherein 7 indicates the flute thickness of the cellulose pad. This is the flute thickness, the gap between the crust and the top, and 5090 specifies the thickness as 5 mm of this flute. The 90 specifies the cross sheet angle. The bisecting angle is the last one. So this 90 can be again 60-30, that is one sheet at 60-degree angle, another at 30-degree, or it could be 45-45. Each pad would have its own performance rating. So any good manufacturer would be able to provide you with the data of what is the pressure drop when you're flowing the air across the cellulose pad for various thicknesses and various air velocities, and what is the saturated efficiency. So let us take an example of the pad which is say 7090 type, and at a typical velocity of say 2.5 meter per second, that is say 500 fpm, for a 100 thick pad, the pressure drop across that pad is close to say 55 pascals. While when you increase the thickness, now it goes to about 80 pascals. If you move ahead on the same table, you would see that at 100 thickness, the saturated efficiency is close to around 65%, while if you increase the thickness to 150 it increases close to 80 to 84%. So you keep on increasing the thickness of the pad, your effect is that saturated efficiency is increasing, that is the supply air temperature is reducing, but your pressure drop on the system is increasing. So you need to then size your blower and motor accordingly to ensure that you are getting the most out of your system. Going by any typical evaporative cooling performance drop chart, you can actually see this in the manufacturer's catalog that if the ambient temperature is say 40 degrees centigrade and the ambient humidity is 10%, you can expect the supply air temperature to be 23 degrees C. While if you increase the humidity to say 50%, the same condition of outdoor 40 degree would result into 32.5. That brings to a very important conclusion that evaporative cooling does not give you a perfect indoor design temperature around the year. There is a wide range of temperature RH which would vary throughout the day, throughout the season, and throughout the year. So the individual who is using this need to understand and factor in while designing it based on the application. This does not replaces all kind of applications, but for a condition like India, it replaces for most times of the years and most of the applications. There's often a question also asked that what is the evaporation or water consumption in the evaporative cooling system. So you can very well design that what is the amount of water which is getting evaporated and what is the bleed off which is required. Now, this is another important factor that while you are actually installing a evaporative cooling system, may it be a hybrid or a direct evaporative cooling system, irrespective of how good water quality do you provide in the sump, the pure water is going to evaporate. But the hardness is going to keep on increasing in the as a concentrate in the sump. Similarly, the dust particles which are coming in through the filter is getting washed off and getting accumulated in the sump, which needs to be frequently bled off. Either you have a automated system using any kind of automation which will allow you to drain off the water after a predefined interval, or you have a constant bleed off cycle. So you can design the total evaporating rate using the same psychrometry phenomena. So if we go back to our old slide of the psychrometric analysis, which indicates our start point of say 40 degree centigrade and 10% RH, on the right axis you would find X2, which is 4.9, which is the humidity ratio grams per kg, and at the outlet, in this case, where the 65% efficiency, the air would absorb moisture. So now the specific humidity has increased from 4.9 to 11.8 kg per grams per kg. You can multiply it with the air density, and that you can come to know that what is the eventual evaporation rate in terms of kg or grams per CFM. So this is how it specifies in the design water, that you first calculate what is the evaporation rate going back into the same psychometric analysis. Then you need to understand that what is the water quality and how frequently you need to drain or bleed off. So the indication over here, E indicates that evaporation and B indicates the bleed off. So your total fresh air requirement would be E plus B. E you can evaluate from the psychometric analysis, and bleed off need to be evaluated based on the water test quality. Now, water test quality can also be done that you take a sample of the fresh water and evaluate that what is the pH level and what is the concentration of calcium carbonate and magnesium, and mark it on the chart on the right hand side. You see over here in this example that you have a pH of 7 and a concentration of HCO3 in the range of somewhere around 150 to 200. So you come to the point over here and take a straight line, draw the straight line from this place from to the left hand side chart and match it to the concentration of CaCO3. In this case, it is between zero point 0.1 to 0.25, which is dropping down. So a CaCO3 concentration is in the range of around 20 over here. So you drop down another line, and the point where both of these meet gives the total ratio of the recirculation versus the bleed off. So when I'm talking of say 0.2, it indicates that if I am having a recirculation rate of 100 liters per minute, we need to bleed off 20 liters per minute. So you add this 20 liters per minute and add it with the evaporation rate to identify what is the total water uh, requirement of the system. So based on this, there are various alternate technologies which are available in the market. It could be a direct evaporative cooling, it could be an indirect evaporative cooling unit, it could be a combination of indirect and direct evaporative cooling, and it could be a hybrid evaporative cooling. What are these? We'll briefly try to touch upon. Direct evaporative cooling, of course, the most common form that you have seen is a desert cooler, which day in, day out we had been using it in particularly cities where it is pretty hot and dry, wherein the water comes in. The oldest examples you can see in the pictures is that people used to keep that surahi, which is filled with the water, and when the water used to come in and flow across it, used to cool both the water and the air. The various simple methods using khas curtains and dropping down the water across it, or using earthen pots, blowing the air from it, or using a desert cooler. They're all based on evaporative cooling with certain efficiencies. So when you design as a air conditioning engineer or HVAC engineer, you normally select either a pad type of cooling system, wherein we just discussed, which is more common because of the less power consumption that it has, wherein you are supplying the air across a cellulose pad, and which is allowing a heat exchange area for the water and air to interact and cool down the air. Or it could be jet nozzle type, which is a case when you're using or applying for an application like, say for example, a textile unit where there is a lot of fluff coming in, so you don't want your pads to get choked. So that is where the nozzles are being used. The only problem being that the water quality has to be properly maintained, and you need to have more energy consumption because now you are pumping in the water to generate that mist. While in case of pads, you are only allowing the water to trickle down by gravity. So the power consumption in those pumps is very, very less in comparison to jet nozzle type. Both has their advantage or disadvantage. Various kind of commercial products are available in the market. The one on the top, you can see four-side suction unit, which is very common now, where you want the power consumptions to be very, very less. They have very low static pressures, as low as around 180 total static pressure, 180 Pascal, while there could be centrifugal type machines, which could be three-side suction. Now, many times people design the air washers without thinking the kind of application. If you don't need a very high level of filtration, there is no point in specifying conventional centrifugal machines with double skin. Instead of that, you can have three-side suction without having the need to increase the insulated panels in the machine, and reduces the cost drastically and the footprint of the equipment. Or there could be a single side suction machine, which is typically used when you actually require to specify a typical level of filtration, because then you have to have a battery of filters depending upon the type of application. There are cases where indirect evaporative cooling is being used. So in this example, what I'm showing you is having a cooling coil connected to a cooling tower. So again, cooling tower is based on the same principle of evaporative cooling, wherein it is not using the air, allowing that air to pull down the temperature of the water. Say if the wet bulb at a given point is 24 degrees centigrade, you are with a range of say 3 degrees centigrade, you are able to achieve your supply water condition from a cooling tower of 27 degrees centigrade, which is getting inside the coil, heating up by taking the heat from the air only sensibly, because here the air is not getting in direct contact with the water or the vapors, and reducing the air temperature from say 42 degrees centigrade to around 30 degrees centigrade or 32 degrees centigrade, and going back into the cooling tower. There is an application wherein both indirect and direct are getting connected, and you have dual stage evaporative cooling systems wherein first you are cooling the air sensibly in the indirect evaporative cooling systems, and then allowing that air to pass by the direct cooling media and reducing the temperature below wet bulb temperature. So this is how a typical indirect direct evaporative cooling machine looks like. The indirect evaporative cooling media could be different by different manufacturers. In this case, it's a cooling coil which is getting connected to a cooling tower and allowing the air to drop down from a temperature of 42 degrees centigrade to somewhere around 30 degrees centigrade. You can see it in the psychometric analysis that, say, at my design point, 42 degree is the ambient triable temperature, and 22% RH is my outdoor air condition. So under normal circumstances, if I would have followed a constant wet bulb line, my supply air temperature would have been somewhere close to 25 degree, assuming that my saturated efficiency of the cellulose pad was around 90%. While in this case, while I'm passing the air through the indirect evaporative cooling media, I'm dropping down the temperature from 42 degree to 30 degree centigrade without increasing any specific humidity. So my total grains per pound or grams per kg of moisture remains constant, just like in air conditioning, but it now changes to a different wet bulb line, wherein my wet bulb temperature goes to 20.5, and again with 85% saturated efficiency, I am able to bring down the supply temperature to 21 degrees centigrade, which in other case could not have been possible because the wet bulb was only limited up to 24 degrees centigrade. So in a dual stage, when the delta T is very high between the dry bulb and the wet bulb, you are actually able to achieve efficiency which is in excess to 100% of the evaporation, and go up to as high as 110 or 115 also. In fact, there are cases where people also go up to two-stage or three-stage evaporative cooling and bring down the temperature to further down depending upon the application. So there are various advantages and disadvantages of using this concept. Just a small comparison of indirect evaporative cooling versus air conditioning. Of course, the power consumption is drastically less, maybe around 20% of what the air conditioning power consumption would be. The maintenance cost would be again less because there is no use of high compressors or refrigerants or electronics. It's operating on 100% fresh air, so definitely the indoor air quality is a lot better. You can maintain positive pressure. You need not have enclosed environment, which is the requirement of the air conditioning system. It dilutes the inside concentrations, so reduces any kind of smoke or foul smell. There's no limitation between indoor outdoor. You can put the, in this case of indirect evaporative cooling, you can put the cooling tower to any other place and connect it with the pump. It doesn't allow the propagation of airborne diseases if you are properly treating it. Maybe having a UVGI lamps to take care of bacterial contamination, if at all, is a concern, and is very, very eco-friendly. But all is not good. So there are some challenges related to using evaporative cooling. It doesn't work well in the entire 24/7, 365 days of the year. There are seasons when it is hot and humid, and in the coastal areas where evaporative cooling doesn't provide a perfect conditions, the inside temperatures in few days might go up to 28, 30 degrees C with the humidity level going up to 70%, 80% RH. And in many cases, it requires to be finalized before the civil layout because the duct sizes would be bigger in comparison to air conditioning, and it needs to be planned in advance. So to take care of most of the similar kind of roadblocks, hybrid evaporative cooling solutions are now available, wherein they have both the indirect direct evaporative units coupled with the air conditioning coils, which can be connected to maybe chilled water or the DX system, and sensing the wet bulb temperature, it can then operate to work on a complete recirculation mode, to work as a regular air conditioning, or on a 100% fresh air mode. Of course, there is some automation which is required. You need to have a mixing chamber with a return air fresh air modulated dampers. But I, as a user of this hybrid evaporative cooling, would endorse that it substantially reduces your power consumption for the entire year and still provides you a perfect conditions across the year. to validate that, some live case studies of indirect and direct evaporative cooling. So this is the one which I've actually witnessed myself. This is for my own space, which I have used way back in 2010 and data logged it using various data loggers in various places across the place. So what you see on the top is the ambient temperature. It shows that how the evaporative cooling is performing throughout the day on the peak summer of May. So on a day of May, when the ambient is 43 degrees centigrade, my room temperature was in the range of 23 degrees centigrade. You see in the morning, while the ambient was around 32, 34 degrees centigrade, my room temperature was also around 28. But as the day progressed, my air temperature inside the room started dropping down, while the outside air temperature started increasing. So at the peak of the day at around 3 o'clock, the temperature rises up to 43 degrees, but my indoor temperature drops down to around 23 degrees. It has to be seen in correlation with the humidity. So if you see the same time of the day and same period, you see that the ambient temperature was say 40 degree, but the ambient RH was as low as 10 to 7%. So the bottom line in the red shows the ambient RH, while the room temperature or room RH is indicated by the blue line on the top, which was ranging around 65% across the day. If you see the combined effect of the temperature and RH, very practically visible, as it's been also seen in the psychometric analysis, that the temperature drops down to around 20 to 23 degree when the ambient temperature rises to 40 to 43 degree. At the same time, because of rise in the temperature outside, the RH also reduces down to 7-8%, resulting into a perfect requirements of the room. When you see it in the entire peak summer seasons of April, you would find that the entire month, this was in 2010, from 5th of April till 5th of May, for the entire one month, you would see that the room temperature was nearly ranging between 22 to 23 degrees centigrade, while the ambient temperature was always from 37 degree to 40 degrees centigrade. When we relate it for the entire season, which is like starting from the month of April to August, you see that the delta T between the dry bulb and wet bulb was very high, and hence the performance of the evaporative cooling system was very good. But as we approached near to the monsoon season, which in my case is around June, so you would see that the outside temperature and inside temperature kind of get merged, and my room temperature more or less remains in the range of 25 to 30 degrees centigrade. When you relate it with the outside humidity, you would find that the outside humidity, which in the month of April was as low as 10%, went up to increase to 40 to 50%, and going forward went to 80-90%, depending upon the time of the day and outside whether it was raining or not, and resulting into a relatively less drop in the temperature on evaporative cooling. So this gives you a holistic picture of the entire evaporative cooling. You'd see that the ambient temperature was, if it was 50 to maybe 20 to 24, my inside room temperature never crossed 30 degrees centigrade. And under those seasons, if I actually switch on the ceiling fan, it kind of gives me a similar kind of comfort which I would have got in a normally naturally ventilated condition. You would, if you refer to the design data book or the ISHRAE weather data book, for each and every city, they have published a very nice graphical representation of the wet bulb temperature. Now, wet bulb temperature, of course, depicts the temperature which, if we are working on a 100% saturated efficiency, we can achieve that using evaporative cooling. By indirect, direct, we can always achieve that wet bulb temperature. So you'd find for a peak temperature of, say, Nagpur, where the ambient goes as high as 44-45 degrees centigrade, the wet bulb never exceeds beyond 27 to 30 degrees. You'd see that the entire year, all these orange dots are indicating 27 degree, and only for few days in the month of, say, May, you would see that it is going up to 30 degrees. Rest of the entire year, it is very well within the comfort range, and you can actually utilize evaporative cooling. You'd find this for each city, and you'd be surprised to see when you analyze that in most parts of the country, barring the coastal regions, you would find the wet bulb temperature to remain well within the comfort zone, or if you consider the adaptive thermal comfort model which we were talking of. Getting back to a case study again for a very small office of 1651 square feet floor plate of the carpet area, if you would have done air conditioning, probably your load was say around 8 ton and you would have consumed about 10 kilowatt of power. Assuming that 10 hours of operation and say 250 days of a year, considering that in winters you're not using the air conditioning system, and a very economical power rate of 7 rupees per unit, which nowadays are in fact more, you would end up spending about 2,25,000 rupees of energy consumption per year. While in case of evaporative cooling, in the similar case where we are using only 6,000 CFM, the power consumption was only 2 kilowatt per hour, resulting into an annual bill of only 42,000 rupees. So the effective saving for a small square foot of 1,651 square feet, you're able to save about 1,83,000 annually, which doesn't include the saving which is related to a backup DG cost or minimum demand charge. And then there are further saving on the annual maintenance cost. So a typical saving of around 2 lakh rupees is what you can assume. The only disadvantage is that you need a floor space of about 85 square feet. If you are able to find that, you are good to go. And it is not as comfortable as air conditioning in case of direct or indirect evaporative cooling for about 20 days in a year on most parts of the country. But if you are doing with a hybrid evaporative cooling, even this is taken care of. So this gives a live example for the same area that I was referring to, that when the outside temperature was 42 degrees centigrade and 22% RH, my room temperatures were around 21 degree centigrade and 24 degrees centigrade. Humidity remains around 60% RH. Similarly, for industry in Pithampur, wherein for about 16,000 square feet of area, the savings was around 26.6 lakhs. Now, these are all live examples and installed about 8-10 years back, and the clients replicating it one after the other. Another proposed complex in Bangalore, where it was a huge commercial complex, where the floor plate was about 1 lakh square feet. The eventual saving was in the tune of 1.35 CR. So you keep on increasing the floor space and you keep on saving in energy bills. That's a huge saving. If you compare it in terms of power requirements, it is dropping down from 85 kilowatt down to only 6 kilowatt. So you can expect in many parts of the country, including say Bangalore, Hyderabad, Nagpur, Pune, Indore, Jaipur, Delhi, all the central part of India to actually deliver perfect conditions in maximum time of the years, and only for the coastal areas where if you are actually using now because of that heat island effect, we see that people residing in and near Bombay, even in Thane, are actually facing this kind of heat island effect and temperatures actually rising than what is being reflected. So there are many case studies which reflect live case studies. Again, a hospital wherein for about 18,000 square feet of area, the saving was in the range of 114 kilowatt hour per hour and giving about 70% saving and saving around 24 lakh rupees per year. So you can find various application. It could be a factory, it could be a canteen, it could be a hospital, a auditorium, a school, a gym, a kitchen, a workplace of workshop or office. Actually, green conditioning finds a place in most of the application. It's only about that we start thinking on what is comfort, educating the end user that what is the thermal comfort that he or she is looking at, and what is the recommended or actual saving that he could expect out of it if he's ready to live in that environment, which is not as perfect as air conditioning, but provides a comfort, reasonable comfort for large part of the year, as large as 95%. Spread the awareness amongst the peers and the clients, and do not always expect the Western world to develop something that is best suitable to you. And that is one single reason you won't find any large MNC coming and talking for evaporative cooling, that because probably their ambient condition doesn't allow them to do that kind of research and analysis. It is only up to people residing in India and the manufacturers and user to actually see that what kind of alternate technologies best suit us, and do not go by thumb rule, always follow the fundamental and you're good to go. So I would thank you. With this, I would end my part of presentation. And for any kind of feedbacks or further information, you can always reach back to me on my email ID, which is nishant@degree.in, or to back office at ISHRAE headquarters to jitender.harsh@ishraehq.in. We'll now quickly open for a question and answer session, and I would request to please keep your mobiles on mute and your handsets devices on mute, and ask questions one by one if in case there are any, or you can mail me you back on that. So if you have any questions, you can please ask me now.
Unmute yourself to ask questions.
Yes, please. Hello. Hello.
Hello.
Hello.
Yeah. Can you hear me?
Hear you.
Hello.
I can hear you.
Yeah. Yeah. This is Jaideep here from Bombay.
Yeah, Mr. Jaideep.
So I put up a couple of questions on the dashboard. Basically, my two concerns. Number one is the consumption of water,
Yeah.
and number two is if we can have some case study comparisons of the hybrid and dual stage versus the regular AC.
Okay, so well, in case of hybrid and dual stage evaporative cooling, the water consumption primarily would not vary hugely, because we are talking of using hybrid evaporative cooling only in the seasons when the outside humidity is very high. So at that point of time, if you go back onto the psychometry and see that what is your starting point, which in your case maybe could be 80%, and my delivery point is also 85%. So effective gain in specific humidity would be almost negligible. So at that point of time, you're running on air conditioning system, so there's no water consumption. Even otherwise, if you would have been running on a evaporative cooling, the water consumption would have been absolutely negligible to be considered. So on terms of water consumption between hybrid and dual stage or direct evaporative cooling, there won't be any major difference. While in case of power consumption, yes, the difference would be there depending upon the ambient conditions.
Yeah, I got that. So you're based out of Delhi.
I'm based out of Indore.
Okay.
Yeah. By the way, I'm not able to see any other questions that you have listed, if at all, on the control panel. If there's anything else that I can help you, please let me know.
No, I'm good. So I'll be talking to you probably separately offline for
Most
some, applications, industrial applications.
Most welcome.
Yeah, I've sent you an email.
Okay,
Oh, okay, thanks.
you're welcome. Any other questions, please? Hello. If there are any other questions, please let me know. Otherwise, we can end this call.
Hello.
Yes, please.
Hello.
Yes, please.
You have said that in the slides that in the hot and humid days, evaporative cooling is can't be not used. Means can't be used. So how we can justify that? Which systems can be used?
Well, in conditions when it is hot and humid, I would like to reiterate the systems can very well be used, but the comfort level would not be as good as what you would get in peak summer or dry conditions. In my case, I'd been very well using it across the year without the need of switching on to hybrid system, but I need to increase the air circulation. As you would understand that for a human comfort on the skin, all the three parameters, temperature, humidity, and air velocity plays an important factor. So when you are supplying the air, which is of higher temperature of say 27, 28 degrees C, and the humidity of around 70, 80%, to give equivalent comfort, you need to increase the air velocity across your human skin, which you can do it by artificially adding the air circulators, which also provides you a reasonable comfort. But if you have any concerns related to it, during that time, you can of course switch on to a hybrid evaporative cooling system.
Okay. Oh, okay. Thank you.
You're welcome. Any other questions, please? In case if there are any other questions, I would be happy to answer them. Okay, so I believe that is what it was. If there are anything else which comes to your mind today or tomorrow, please feel free to connect back with me. It was a pleasure to be with you, and I look forward to interact with you in future. Thank you very much. Jitendra, you can please call it off.
Yeah, thank you, sir. Thank you so much for this webinar, great webinar. We got a good response and good attendance. The total attendance was around 70 in the complete session. So, and the recording will be available in the YouTube ISHRAE TV very shortly. So, please share your feedback on this mentioned email IDs. Thank you all, and thank you, sir.
Thank you. Thank you, sir.